Welcome to week 14. We're going to be continuing our discussion of differential equations. This week we're going to focus on linear first-order differential equations. So to start with, let's look at what that means. So I'm going to write down the general form of one of these equations. And this could be dt, whatever your independent variable is. So let's break this down. This is a first-order differential equation because the highest order derivative is a first-order derivative. It's linear because there's no higher powers of y. We only have y to the first order. So notice here that we have p of x and g of x. Those are our two different functions of x. And the coefficient to this term is 1. Now, it can certainly be the case that an equation could be written so that there's something besides 1 here, but before you start the process of solving an equation like this, you want to go ahead and divide through by whatever's here so that there's a coefficient of 1 right here. So say if this was x squared, go ahead and divide every term by x squared. So why do we care about this form of equation in physics? Well, one example is when you're looking at electric circuits. So lots of differential equations come up when you're solving electric circuits that have capacitors or inductors in them. So if you look at the example, and this example is one of the exercises in your book actually. So let's say you have a circuit with a voltage source, and here the voltage is a function of time. So let's say that's v of t. This squiggly right here is the inductor. So we show that with a symbol L, and over here we've got a resistor, which I'm sure you already know that. So if we look at the voltage drops around the entire circuit, we have voltage as a function of time, and the voltage drop across an inductor is given by this expression. Then I'm sure you're all familiar with the voltage drop across the resistor. So this is what we get from doing Kirchhoff's laws. We can rearrange this so that it looks like the form of equation we were just looking at. So here time is our independent variable. And as I said, if you have something in front of your first derivative term, you need to divide through by that. So I'm going to divide every term by L. And you also notice that I'm writing, instead of writing IR, I'm writing RI just to fit the form of this equation better. Obviously, it doesn't really matter. If we wanted to solve for the current as a function of time, then we would need to solve this differential equation, which is a linear first-order differential equation. And as I mentioned last week, the reason we did second order first was because that particular form of equation was easier to solve. This one looks like a bit of a mess to solve. You have to do a couple of integrals to solve this sort of equation. The procedure you have to follow to solve this sort of equation is really not obvious. So I want to spend a few minutes talking about where that procedure comes from. I'm going to recopy our equation this way. So if we just consider this form of our equation, and we want to figure out how to solve this equation, we want to find y of x. To solve this equation, you need what's called an integrating factor. That's when you multiply through the whole equation by a factor, and then it becomes an equation that you can integrate. So the integrating factor, I'm going to call mu. I believe your book calls it I. It's the same thing. So you have to multiply the whole equation through by e to the integral of p of x dx. As I said, this is really not obvious, but my goal is that you see that this works. It took a lot of clever mathematicians to figure out that this would work in the first place, and I don't expect you to figure all these things out from scratch. So let's multiply this through. So we have, okay, so once we multiply this factor through on both sides, then it's possible to integrate this left side of the equation. I know it doesn't look like it should be easier, but it is. So we're going to integrate both sides. And it actually turns out that the integral of this is this. In a minute, I'm going to have you take the derivative of this to prove to yourself that this is true. Now I'm going to use this expression to make this a little bit less cumbersome to write. So then if we're just looking for y of x, we just solve this equation. So what this tells us is that when you want to find y of x from a linear first order differential equation, you have to find the integrating factor. That requires doing an integral. And then you do this integral of g of x times that integrating factor and divide that by the integrating factor. Now when I first learned this, I found it really unsatisfying. It all felt like magic because it seemed like a lot of cleverness I never would have thought of. And unfortunately, the solutions to a lot of differential equations looks like that. You can still get used to doing the procedures, and you can see how they work out so you can believe them. So to help you believe that this works a little bit better, as I said, we're going to go back and look at this step that happened right here, so you can prove to yourself that at least this integral gives you this. And we're going to do that by doing the derivative. So this is what I want you to do. So what I want you to do is take this derivative. So notice when you do that, you're going to use the product rule because you have y of x times e to the integral here. And you're going to have to do the chain rule for this exponent. All right. Go ahead and try that out. And then press play when you're ready. Okay, so we're going to do the product rule. So first, we're going to have the derivative of dy dx, and we're going to leave the exponential alone. Then we're going to leave y of x alone, and we're going to take the derivative of the exponential. So we have to do the chain rule, which means we have to take the derivative of the exponent, and then we have to do the derivative of the whole thing, which basically means the exponential stays the same. Because taking the derivative of exponentials is pretty much the easiest one to do. Alright, let's look at this a little bit more. So dy dx, that's y prime. And I hope you can see that if you take the derivative of an integral, you just get the inside function. And then all we have to do is factor out our integrating factor. Okay, so that at least shows that this works out. But let me know if you have any questions about this. So the next thing we're going to do is we're going to do an example. I'm going to show you how we actually can use this result then to solve one of these types of differential equations. Alright, here is our linear first order differential equation. The first thing I always do is write out what p of x and g of x are. Alright, now that we know that, we can do the first step. So step 1 is find the integrating factor, mu of x. So first we need to do the integral of p of x dx. Alright, so this is just 2 log x. At this point you don't need to worry about your plus c's. So this gives us that integral, but remember the integrating factor is e to this integral. So we have e to 2 log x. Now we can simplify this, and we definitely want to. So let's look at how we do that. But you can do it this way, where you remember that when you have two numbers multiplied together in your exponent, it works like this, and e to the log x is x, so you get x squared. Or you could remember a property of logarithms that 2 times log x is the log of x squared, and then you could use that the exponential and log are inverses of each other and pull the x squared out that way. It's pretty nice. it's fun to put log in these p of x's because then everything cleans up nicely. Okay, the next step we want to do is find the integral of g of x times mu of x. Alright, so that is this. Now you want to remember to use your plus c. It actually works out because the integrating factor is on both sides of the equation, that even if you did include the plus c in your original derivation, it would cancel out. But this plus c does not. I'm out of room on this page, so I'm going to move on to another page to write out the rest of this one. So step 3, plug in the whole formula. So remember, that's this integral divided by the integrating factor. So we have, in this case, we just did the top integral, and we divide by the integrating factor. Now I'm going to go ahead and simplify this. So one thing I want you to be careful about here is where your plus c ends up. So when you're just doing integrals in isolation, you just have a plus c. You can tack that onto the end of your answer, no problem. But when you're solving differential equations, plus c is going to appear at some point in your process. But depending on where it is, it may have another factor multiplied by it. So this c is divided by x squared. So don't think that you can just tack on plus c to the end of your answer. It doesn't work that way. So this is our general solution. And then we would need an initial condition or a boundary condition to solve for c. Now I'm going to give you 2 examples to work out for yourself so you can get used to doing this process. And I hope that since we went through where this comes from, that makes this a little bit easier to remember. But again, I totally understand if it seems like a lot of cleverness and that bothers you. That bothers me too. But this is physics class. We are not being clever mathematicians, we are being clever physicists. Alright, so here are your 2 to work out for yourself. And just a reminder on this number 2 here, the coefficient to your y prime term needs to be 1, so divide through to make sure that that's the case before you begin solving. Alright, remember you're solving for the general solution, y of x. Alright, so take a few minutes and work these out for yourself. Press play when you're ready to go. So we've come to another case again where the work is just not going to fit all on one page. So I'm going to go to the next page to work out these examples. Okay, so what's p of x? 3 over x. And g of x? Okay, so first thing we need to do is do the integral of p of x. Well, this looks very similar to the example that I did, actually. Because, you know, it's so fun to use logs. So our integrating factor, then, is e to the 3 log x. So if we follow that procedure through again, we have e to the log x cubed. So what do we have? X cubed. Alright, that's a nice integrating factor. Next thing we need to do, take the integral of g of x times the integrating factor. This is a pretty simple case. It's nice. Remember your plus c. So then our final answer is this integral, so that gives us x squared over 2 plus c divided by our integrating factor, x cubed, and if we clean that up, we get, okay, so that's our final answer. Let's do the last one. Okay, so we need this coefficient for the y prime to be 1, so we're going to divide the whole thing by 2x. So p of x is not 1, it's 1 over 2x. And g of x is not 2x to the 5 halves, g of x is x to the 3 halves. Alright, let's integrate p of x, which means our integrating factor is x to the 1/2 power, or the square root of x. Now we need to do our integral of g of x times mu of x. Now, I've given you some examples to try for yourself that work out pretty neatly. One, because this log trick is pretty neat and gives us nice answers in the end, but I've had students in the past who are just pretty rusty with their logs and they need more practice with them. And two, because I don't want you to be so bogged down in messy algebra that you're missing out on the main point of how to do this procedure. Okay, so then our final answer is we take this integral, so we have x cubed over 3 plus c, and we divide by mu of x, our integrating factor. So we clean this up. All right, so there you go. That's our final solution. That's where we're going to stop for this week. So let me know if you have any questions in the problem solving discussion, and I'll see you next week.